Okay, the second one we're going to talk about is Charles' Law, lesson 5 here. Charles' Law says the following. If this volume changed while maintaining a constant pressure, the temperature also has to change. We know that when we change temperature, we change how fast the gas molecules go, right? How fast they move. The higher the temperature, the faster they go. The lower the temperature, the lower the temperature, the slower the molecules go. It's the end of the day, okay? This is important here. Charles' Law says volume goes down, temperature goes down. Volume goes up, temperature goes up, okay? And you can think about it in this way here, okay? So that's the important parts there. If you had these two cylinders again, and I'm going to use these kind of a little bit here, but if you have these two cylinders, and we have this volume here, okay, whatever that is, and we're going to talk about temperature as well. And if I take that and I cut it in half again, let's just say, for example, I don't have to cut it in half, but whatever. If I decrease the volume, and here the volume's kind of large, okay? If I have my 5 gas molecules here, and they're going, well, let's say, fairly fast in this case, I might get a pressure of whatever. The pressure has to remain constant here, yes? Pressure is constant. You could even pick a pressure, like maybe say 1 atmosphere or something, or 1.325 kilopascals, or 14.7 psi, or 760 millimeters of mercury. Okay? The pressure has to stay the same. Well, if I decrease the volume, and I still have my 5 gas molecules in there, okay, what do I have to do? We know this. If I decrease the volume, what happens to the pressure? It goes up. How do I not let the pressure go up? Well, I have to slow these down, right? So now I slow them down so that, again, I have less space, but I need to get them to have less collisions, yes? So I have less collisions by slowing them down. So if the volume goes down, the temperature has to go down. If the volume goes up, the temperature has to go up, okay? And that's Charles' Law. Now, Charles' Law is, I've got a lot of information here, actually, and there's a lot of things to go with Charles' Law. So we're going to talk about that as well. It's just not that, of course. But that's basically the idea. If we want to keep the same pressure, then if the volume's large, I have to have those molecules moving fast so that I create 100 kilopascals of pressure. But if I sink it down into this section, now those molecules with the pressure would go through the roof. Unless, of course, I slow them down. So I have to take temperature away. I have to take energy away from the molecules. I have to slow them down so there's less collisions. That's Charles' Law. Okay? Now, this is demonstrated graphically. You need to know both of these graphs. Absolutely. This one is temperature here in Kelvin and volume. Okay? That's one of the options you're going to see. And the other one's going to look a little something like this. Temperature in Celsius and volume. Make sure you know both. Both are important. Okay. Is that good? Okay. They represent the same thing. There's a relationship, of course, between volume and temperature. And we're going to talk a little bit more about that coming up here. Okay. Somebody asked me this question yesterday. So we're going to answer that today. Okay. Before we get to that, though, I'm going to skip a little bit here, and we're going to go right down to here. Okay. So I'm not sure if you guys have the formula here or not. This is a little far ways down here. And then you're going to see ABC. So you should see kind of somewhere here, you should see demonstrated mathematically V1 over T1 equals V2 over T2. Okay? And it says here that the pressure has to be the same, has to remain constant. The system has to be closed, And in this case, they tell you the temperature has to be in Kelvin. Okay. Yesterday, we looked at how to convert to Kelvin and back to Celsius. That was a whole last column, yes? So we've done this. Why does it need to be in Kelvin? Look at the temperatures. Look where these are. Okay. Here's T1 and T2. Initial, final. Yes? Initial on this side. No, can I do it? No. Initial on this side, final on this side. What would happen if I use Celsius as the temperature? What would happen if I use Celsius and plugged in a Celsius value for one of these two here? What could happen? What do you think? Think about Celsius. Think about Celsius, yeah? Yes, you would have, today is -7 Celsius, yes? Apparently. I don't know. If I put -7 Celsius here, what does the volume potentially become? It becomes, and I put other numbers in here, this is -7 and I solve for V2. What happens? V2 becomes what? Negative. So if I have 10 liters of a gas, and then I do this test at -7, I have negative volume below? No, that doesn't make sense, right? So we can't use Celsius. What's the other number that could create an issue here? On the bottom, huh? I didn't hear. No? Well, yes. We're not American. But yes, Fahrenheit would be another issue. No, but what's a number that's going to give me an issue with this? Yeah. Yeah. What happens if you put 0 into the denominator? We call this the denominator, right? Denominator. I'll be back. I know that because it's T2. Terminator. I'll be back. Denominator. That's what I'm doing. I'm doing that here. Like, hey, I'm doing this here. You're supposed to be laugh. Denominator. T2. I'll be back. That was actually probably T1. Anyway. Highly recommend. Anyway. T1, T. If you put 0 in the denominator, what happens on your calculator? What happens if you take 4 divided by 0? Error. Or undefined. Yes? Not 0. Undefined. Right? Error. It's impossible. 0 times any number is not going to give you 4. Right? So we can't put 0 in there. So this is what happened. Okay, listen. So they said, okay, look. There's a relationship. He says, this guy came along, he said, hey, look, guess what? There's a relationship between volume and temperature, I promise you. Okay? I guarantee it. If the pressure has to stay the same, the more volume I have, the faster the molecules go. The less volume I have, the slower they need to go, okay, to keep the same pressure. So he decided, hey, I'm going to graph some gases. So he grabbed some gases and he did this. Watch. And he started to graph them. So he did the first graph here. This is volume, and this is temperature in Celsius. And he graphed the first one. Maybe he took some hydrogen, and he started to graph it. So he said, okay, what's the volume at this temperature? What's the volume at this temperature? Remember, the pressure has to stay the same. So this pressure is 100 kilopascals, no matter what. Okay? What's the volume? What's the temperature? What's the volume? What's the temperature? And he kept going and going. What happened over here eventually, and this is important for you to understand, and this is Unit 1. What happens when I cool the gas down enough? Pay attention. It becomes what? No, not quite. A liquid, yes? And of course he's studying gases, so he gets to this point right here and he says, oh, darn it, it turned to a liquid. Okay? Because when we take energy away from molecules that are going like this, when they start to slow down, they become attracted to each other, and then they become a liquid. So it turned to a liquid. And he said, okay, good enough. I'm going to stop there. He grabbed another gas, some oxygen gas, and he did the same thing. And at some point, it turns to a liquid. Okay? Not maybe the same point, but somewhere, maybe less or higher. He grabbed some nitrogen gas, and he did the same thing. Okay? And maybe that one he got a little lower. Maybe he got down to there kind of thing. And he did this with a bunch of different gases and then used some scientific experiments or scientific knowledge that he had and said, hey, wait a minute. All these gases seem to kind of converge or kind of come to the same spot. He said, hey, if I continued this on, and if I continued this on, I kind of bent that a little bit there, I apologize. And if I continue this on, they all seem to kind of come to the same area there. They all kind of come to the same number. And he said, well, what is that number? And he said, well, that's probably going to be negative 273.15 degrees Celsius. Okay? Now, here's an important thing to, and please know this, because I hear this all the time. We hear this term all the time and stuff. But they all seem to kind of meet here. What does this mean? If the gas actually gets down to negative 273.15 Celsius, what does that really mean? And the answer is, it means all motion stops? No. What it means is the gas would have what volume? 0. Right? Correct? If I cool this gas down, and if I was able to keep cooling it without it turning to a liquid, when it gets to here, that volume is 0. Right? That's the 0 line. So that gas would also all of a sudden have no volume. It would just disappear. Because we know from the 5 properties of gases that all gases have to take up some amount of space, right? They're occupying this space right now. They take up a space. Well, if we did this, it's saying that gases all of a sudden disappeared, gone. Okay? And that there'd be no more gas in that container. And we know that that's not possible. So he said, theoretically, they would have 0 volume at this number. And that's not possible. That's impossible, as Homer Simpson would say. Okay? Impossible. So, let's change this a bit. Instead of using, all he did was say this. Look, if this is negative 273.15, and I don't want any negative numbers, I'm just going to do this. Watch. Negative 273.15 is that. How do I get no negative numbers? Watch this. Owen. No. Oh, can I do this? No. This worked better last class. Not going to lie. I don't know. Can I do this? Let's see. Nope. The point is, okay, so what he said was, hey, if I don't want any negative numbers, let's just take this and add 273.15. Hey, add 273.15, and we'll call it 0 Kelvin. So he just slid that over, which is what I was trying to do. He just slid that over and said, hey, let's call that 0 Kelvin. So that becomes this number right here. And again, this number is theoretically impossible. So since it's theoretically impossible, we're never going to be putting 0 in our formula, and we're never going to be putting a negative number in there either. It's going to start at 1 Kelvin and go up from there. Okay, or less, well, 0.1, whatever. You know what I'm saying. Okay? So that's how we came up with the Kelvin scale. And that's why this formula now works. There's still a relationship. So going back to here real quickly, I want you to remember this, okay? Charles determined that all of his gases would have a theoretical 0 volume, means they would have no volume at negative 273.15. That's what that means, okay? This is the temperature that Charles labeled absolute 0. That's what absolute 0 is. It's not, people always, well, can we cool something down to absolute 0? Yeah. Does that mean everything stops and you're frozen and frozen, everything stops? No. It just means that we have no more gas now all of a sudden, which is impossible. So that's what it means. Okay, yeah, yeah. Okay, so that's where the scale came up with. And then he said, okay, well, I'm going to change that. I'm going to say negative 273.15 is the new zero. And I'm just going to add 273.15. And that's where the number came from, yeah?
So what if you made a gas negative?
Well, you can't, though. That's the problem. They'll turn to a liquid before that. So that's the issue. Yeah.
Would that to be due to a liquid or a solid instead?
Again, it depends on their. We don't have stuff for that. Like we don't. Like there's no absolute zero for that kind of stuff, right? Again, if you, in a lot of cases, we probably would never get this cold anyway.
Yeah.
So, I mean, at some point here it'll turn to a liquid. At some point it'll probably turn to a solid, right? Before we even get to that point anyway. So, all right. So again, this is an example of Charles' law here at work. And again, we should look at these diagrams. This is on the back or something there for you. But we should look at these diagrams and be able to explain what's going on. In this case here, remember we talked about equilibriums. That is equal to that right now. If I start to heat up the gas, they start to go faster. Okay? So the temperature increases. The temperature increases, they start to go faster. There's more collisions, there's more pressure. Outside, there's not as much pressure. As a result, what has to happen? Those two pressures are not equal, so the disk has to move up until, again, the atmospheric pressure and this pressure, those two things equal out. Okay? It's got to create more space until those two become equal. Okay? Good? Questions?